Before we start with the main components, the main mechanisms of the model, I want to briefly explain you how the model is set up, so the initialization, and then we will have a first look at the at a run of the simulation, that you get an idea about the concept of the simulation itself. First of all, if you zoom in here in the in this part of the model, we have here the C# initialization component that defines the location of my first inhabitant and the first workplace in my model city. So you see the variables that I use in the following are population distribution and workplace distributions. So I have a stock of populations and a stock of workplaces that depend on each others, which of these cells is more attractive for new people if the city grows. So this is a model for a growing city. So at the moment the gray cells are empty, and when I run the simulation, people move into the city, into this grid city, and they select the place where they think it's best to live at. And the initialization of the model, if you open this script window, zoom in here, what we do here is we place the first inhabitant. So this is this line of code, population distribution equals to 1 and workplace distribution equals to 1. These are the first workplaces, the first workplace and the first person or the household that lives in the city. How to do it? You see here I have an input of a point. If I enable the preview, you see that's the point located here. You can draw a point in Rhino and reference it to the geometry component and then link it here. Then you can change this location, but for now I will use this point. And what we do in the script is, so first we declare our lists, our variables, and the list of population and workplaces. And then we look for the cell that's closest to my reference point, because that's the place that I can define manually where I want to have the first person to be located in my city. And this loop computes the minimal distance or finds the cell that's closest to this point. So I go through all the points because my cells are represented as a list of points, the center points of the cells. And then I test the distance to the point and I remember the minimal distance. And after I tested all the points, then I found the minimal distance and I know the reference index of my central point of my cell. And this reference index of my list of points is used here to say, okay, in this cell I have one inhabitant. And how I store this is done very simple. I always use the same order as I have the order of point 3D in my list. That's what's from the points that I created here in the grid. So this list, this is always used in the same sequence, in the same order, and I send it here to this initialization component, and also the distances are computed based on this sequence of points. Okay, so this component is basically doing nothing else than placing the first inhabitant and workplace in the list, which is otherwise empty. So here, if you move your mouse over this variable, you see you have 80 variables. You remember I have 80 cells in my system, and they are all 0 except here it's the second ID, which is then 1, means there is the workplace. Okay, now I close this window, and to explain you the basic idea of the model, I activate the loop. What you see after I activated my loop is the result of the first iteration of the model because the output of my population distribution is linked to my visualization, which you find down here. So the number input, which is used to color the grid, that's at the moment my population distribution. And this means the attractivity for my population, respectively the current distribution after the first run, is shown here. So the red cells are the ones with the highest number of people in it. So that's a little bit different than my initialization, because what I've done is that I distributed already a few people. I could also show the potential. This is then what I have had in the beginning with my initial population equals to 1. That's the attractivity for new people coming into the city. So here you see the attractivity of the population for new people, which is shown now in this map. So the warmer the color, the higher the attractivity for new people. And then after I distributed 10 people, it looks like this. How this works, we will see in a minute. I would just want to show you how the system, how the simulation runs if I run it over a few iterations, so 50 iterations. And you see the development of the population density or the distribution of households of people in a city. And the visualization is done in a way that the maximum value is always red, even if it's only one person or 100 or 1000 in a cell. That's the red cell with the highest value, and the value of the highest or the biggest number of people is what you can find here in the output. At the moment it's 77, what you see here, and now here we see it's run for 100 iterations. The idea of the simulation is that I have here a script that tells new people coming into the city that places that are close to other people are more attractive, and places that are closer to workplaces could be more attractive. So in this component I basically store the logic of the attractivity maps, means which location is more or less attractive for a certain land use. My land use is residential usage, people. And I have the work distribution. I do the same thing with computing the attractivity for new workplaces. We can always visualize the attractivity maps just by wiring the outcome of the attractivity. So here the workplaces also want to be close to people, because if you have a factory or an office, it's good if the people live nearby, then the workplace is more attractive for them. So they try to be close to the people. But also people want to be close to the people, so there is a kind of competition for the places that are most central in my city. That's why you usually have the high density in the city center. And in this component I implement the logic how new people, how new workplaces are added to the system, and that's then looped so and so many iterations. We will look in the next step how the attractivity calculation works.